Welcome back. So in this lecture, our focus is going to be on quantum statistical mechanics. In classical stat mech, we had already derived an expression for the probability of being in the microstate with an energy E, right? And in classical stat mech, we also realized that essentially for a given macrostate, which is characterized by E, V and N for a hydrostatic system, and more generally E and X, where X denotes the generalized coordinates, there lies an infinite possible number of microstates. And from the basic and from the foundation of first principle of statistical mechanics, that is identifying the entropy Kb as ln times omega, we could derive the probability density of the system being in a microstate with an energy E, right? But in quantum stat mech, things are little different. For a hydrostatic system, if you take n particles in a box, then the classical stat mech, I know that Ri and Pi, the set of coordinates and the momenta, form a microstate. But in quantum stat mech, we cannot have such an identification because it's not possible to simultaneously measure the coordinates and the momenta. Further, whereas we had a trajectory in phase space in a classical stat mech, in the classical picture, this is replaced in quantum mechanics, this is replaced by a wave function. Now consider a hydrostatic system with the macroscopic variables E, V and N, right? The wave function of this system is denoted by where Rn is the set R1, Rn, and this defines the set of momenta of these particles. This is an isolated system, right? We'll consider it to be an isolated system, and the evolution of the wave function follows the Schrodinger equation, which is well known to all of you, is given by h hat psi, where h hat is also a function of Rn Pn, is the Hamiltonian of the system. The evolution, the time evolution of this, I can solve this equation and I can simply write it down, is equal to psi of Rn Pn e to the power minus Et over h bar, because the energy E of the system is conserved, so that the time independent Schrodinger equation obeys. So this is the eigenvalue of the energy equation, so you write it down as E times psi of Rn Pn, right? So one has to identify that this is the eigenfunction of the energy, and therefore this becomes the eigenfunction of the energy. Now typically the solutions might have discrete energy levels, so this can have discrete energy levels if you consider one particle or two particle systems. However, if you are considering a macroscopic system, with a large number of degrees of freedom, then the difference between the respective energy levels is discrete energy levels decreases, and you have a continuous spectrum of energies. There are often degeneracies also, and for a given energy, therefore, you can have a more than one wave function, right? So it is also worth noting that in a macroscopic system, it is not always possible to know the exact values of the energies. So you can always allow for a certain uncertainty delta E in your energy. Just as we had allowed in the classical case. So essentially, you are looking at an energy between E and E plus delta E, right? And there exists a lot of microstates between these two energies. So the microcanonical ensemble in quantum systems, in quantum stat mech, is essentially counting these number of microstates that lies between the two energy levels E and E plus delta E. So we will write down O omega E as GE times delta E, where this function that we have is essentially known as the density of states. Now therefore, in quantum mechanics, or rather saying that in quantum statistics, instead of averaging over all the phase points that we did in the classical case, what we do is we average over all the wave functions that exist within an energy, within the energies E and E plus delta E. However, one should note very, very carefully that if you are measuring however, a microstate psi I E of, or let's say we'll just denote it as psi I E, does not yield a definite value of a physical observable, right? And let's say we denote that observable as RI PI. Rather, what you get is you get an average with a certain probability. So you get a value with a certain, so you measure a value with a certain probability. To be more explicit about this, we consider this phase space observable f of Ri pi, and this corresponds to a Hermitian operator. F hat. Why Hermitian? Because it's a physical observable, and therefore you realize that the operator must be Hermitian, so that the eigenvalues are real. It has, so since it's a Hermitian operator, therefore one can write down its eigenvalue equation as Fn phi f of n. Now each eigenvalue of Fn corresponds to a possible measurement of F, right? So each eigenvalue of F hat, this corresponds to a measurable value of the observable quantity f of Ri, comma Pi. Now, in a measurable state, in a microstate, psi e of I, let's say, the measure for, damn it, therefore, in a microstate, psi I e, one measures Fn with a probability phi n psi I, which is integral d cube r1 d cube r2 so on phi n f star rn psi I e star rn. One can see this just by expanding the wave function in the basis psi e of I is equal to Cn phi n, where this one phi n, the eigenfunctions, form a complete set, and Cn are the probability amplitudes. They are the probability amplitudes given by phi n psi e I, right? Now, if one performs measurement of the observable f of Ri Pi, so if I perform the measurement of this observable, let's say, in a set of identical systems with the same microstate psi I, so measure this in a set of systems with identical microstate so we will say identical systems with the microstate in a set of identical systems with microstate with the same microstate psi e of I, then each of the eigenvalues occur with a probability amplitude. Each of the eigenvalues with a probability amplitude of phi n psi e I. In quantum statistics, so one can write down this psi e I f is dr1 dr2 drn psi e star I rn f ry pi psi e I rn, right? Now, in quantum statistics, another average adds to this. One is no longer able to tell which specific microstate psi ei the system assumes. So on top of it, so when I measure this operator, this physical variable, I get a value, the eigenvalue, with an average psi ei f hat psi ei. But on top of this, you will have in quantum statistics, you will have another average that adds to it. And why is that? Because you cannot say which microstate the system assumes, right? So one can only give a probability. So there is one can only give a probability rho I with which, well, the system, well, rho I of finding the system in the microstate right? If now one performs a measurement of the observable in a set of such identical systems, one can measure only the average of the quantum mechanical operator f cap or f hat weighted by this probability. So the average, the expectation value of this is going to be sum over rho I psi ei right? This, however, is not the general expression. So I hope it is now clear that where the difference that this average comes in, right? So if I start measuring a physical observable f in identical systems with the same microstate, then it's not, I will get the eigenvalues fn, we saw fn with a certain probability, right? So I measured this, but now the problem is you have prepared the system. When you write down this, you have prepared the system in a given microstate. But in reality, when you measure it in a system, this may not be so. The system can be in any microstate, right? And one cannot definitely say, look, the system is in this particular microstate psi e of I. It can be in a different microstate. So therefore, one can only give a probability of rho I of finding the system in a given microstate. And once you have this rho I, this probability, then your actual expectation value or the average that you measure is a weighted average of this. And this weight factor rho I is the probability of finding the system in the microstate psi ei, right? The most general expression, of course, is given by f hat is sum over rho ki psi ei f hat psi e of k. The rho ki is now to be interpreted as a probability which the matrix element is the probability with which the matrix element contributes. So the matrix element of this that we had written down, psi e of I f hat psi e of k contributes towards the statistical average. So this quantity that you have written down over here is the statistical average, and this is the quantum mechanical average that we are familiar with. So we have the statistical average of an physical observable, which was given by sum over I rho I psi e I f. This was the microstate in which we assume the system to be, and this is the Hermitian operator corresponding to the microstate, corresponding to the physical observable Fri Pi. And we said that the general expression, this is not the general expression, the general expression can be written down as rho I k psi e I f hat psi e of k. And this is not the general expression. The general expression is I comma k rho of ki psi e I f hat psi e of k. To see how we can go from this to this, one can expand the microstate as Cn phi n, right? And therefore one has Cn I star phi n, where Cni is equal to phi n psi ei and Cn star I is equal to psi ei phi of n. So if we use this now and expand, then we come up with f hat as sum over I rho of I sum over n comma n prime. We will have Cn star of I phi n f hat phi n prime and a Cn of I, right? Sum over n comma n prime rho of n prime n phi n f hat phi n prime, where the matrix elements rho n prime n is given by sum over I rho I Cni Cn star of I, right? Sorry, this has to be, please be careful with this Cn prime Cni star. Now if I look at this particular expression, now I can interpret rho n prime n as the matrix elements of an operator in the basis phi n's, so that we can write rho n prime n is equal to phi n prime rho hat phi of n, in which case this average this statistical average, this is, please note that this is the statistical average that we have said earlier also. This quantity then becomes sum over n prime phi n prime rho hat phi n f phi n prime. One can use one sum over the n and use the completeness of the basis to come up with the result n prime phi n prime rho hat f hat phi of n. The statistical average of this physical observable becomes this, right? In other words, this quantity is trace of rho hat f hat. And it is to be noted that the trace is independent of the choice of the basis. Further, the average, the general expression for this quantity f hat becomes diagonal if one uses the eigenfunctions of f hat or rho hat as a basis. It's important to realize, so therefore what we have over here is essentially trace of rho hat f hat, which is sum over k phi k rho cap f cap phi k, right? It's important to realize therefore that this quantity rho hat performs the same role as the classical probability density, right? Where we had the classical average f classical was 1 over h to the power n d of xn rho of xn times f of xn. So this was my classical average and this is my statistical average. And I mean, you can write it down in terms of integrals over coordinates, that is also okay. Then you will see that this performs the same role as the classical probability density. So now we want to discuss pure and a mixed state. So if a quantum mechanical system is in a single state psi of E, right? Then this is called a pure state. In contrast, if a system can be in any of the states psi of E I with probabilities rho I, then this is called a mixed state. Now, given the system is either in a pure state or in a mixed state, all the quantum mechanical and statistical averages can be calculated, can be determined for any observable, provided we know the form of the density matrix, right? If the probabilities rho k prime k are known, then rho hat, the density matrix, in any arbitrary basis can be written down as rho hat is equal to sum over k comma k prime phi k prime, rho k prime, k phi of k, right? Now here the diagonal elements which is phi of k, rho hat phi of k, they denote the probabilities for the system to be in the state phi of k. In contrast, the off-diagonal elements, which are essentially phi k prime, rho hat phi of k, they denote the transition probability of the system to go from state phi of k to phi of k prime. You prepare the system psi I, right? And the set psi I, they form an orthonormal set, such that if you prepare the system in psi I such that your rho II is non-zero, the diagonal elements are non-zero, but rho ik is equal to 0, which means there is no transition between the states which are allowed. Then your rho hat is sum over I psi I rho II psi I, right? So here this sets, they are an orthonormal set, right? Which can always be done if you start off not with an orthonormal set. You can always orthonormalize them by using the Gram-Schmidt orthonormalization procedure, right? Please note that these do not form a complete set. They do not span the whole of the Hilbert space, but a subspace of the Hilbert space in which this state vector is precisely the state vector is not precisely determinable. For a pure state, rho II is equal to 1 for only one index and is equal to 0 for all others. In this case, your density matrix takes the form psi E. We will now simply the sum is now removed because rho II is 0 for all others, and for only a given value of I you have this rho II is equal to 1, which means the probability of finding the system in that particular state is equal to 1. You are certain to find that there, and all the other probabilities are 0. Therefore, for a pure state, your density matrix take this particular form. Now this quantity essentially forms a projection. It's a projection operator for this state. So rho hat is the projection operator for the state, and the respective and the subspace is one-dimensional.